In the vast expanse of mathematics, there lies a captivating realm known as linear algebra. This branch of mathematics is not just a collection of abstract concepts, but a powerful tool that has real-world applications. It's a field that empowers us to unravel the secrets hidden within complex systems, providing a framework to understand and manipulate the world around us. From the intricate workings of the cosmos to the elegant algorithms powering our digital world, linear algebra is everywhere. Linear algebra is the language of relationships, describing how things change together, how they interact, and how they transform. It helps us model and predict behaviors in a variety of systems. At its heart, linear algebra is about solving equations. These equations can represent anything from simple problems to highly complex systems. But these aren't your ordinary equations with single unknowns. They involve multiple variables that interact in intricate ways. We're talking about systems of equations where multiple variables intertwine and influence each other, creating a web of relationships that can be both challenging and fascinating to untangle. Imagine trying to predict the weather, where temperature, humidity, and wind speed all play a part. Linear algebra helps meteorologists create models to forecast weather patterns accurately, or simulating the movement of a flock of birds where each bird's trajectory is affected by its neighbors. This requires understanding the complex interactions within the group. Linear algebra provides the tools to tackle these intricate problems, offering methods to simplify and solve them efficiently. It allows us to organize information efficiently, perform complex calculations, and extract meaningful insights from mountains of data. This is crucial in fields like data science and machine learning. This powerful framework underpins countless fields, from computer graphics and engineering to physics, economics, and even the enigmatic world of quantum mechanics. Its applications are vast and varied. Join us on a journey through the fascinating world of linear algebra. We'll delve into its core principles and explore its wide-ranging applications. We'll explore the fundamental concepts, uncover their hidden beauty, and witness their remarkable applications in shaping our understanding of the universe and our place within it. Together, we'll unlock the secrets of linear algebra and see how it transforms our world.
Imagine an arrow. Picture it in your mind with a clear point and a defined length. It has a length and a direction. This arrow isn't just a simple line, it has a purpose and a path. This simple object, known as a vector, forms the bedrock of linear algebra. Vectors are fundamental tools in mathematics and physics. Vectors are mathematical entities that represent quantities possessing both magnitude and direction. They are essential in describing various phenomena. They extend our familiar number line into multiple dimensions, allowing us to describe positions, movements, and forces in space. This multidimensional aspect is crucial for complex calculations.
Think about navigating a city. Every turn and every step can be broken down into vectors. You might say, walk 2 blocks east and then 3 blocks north. These directions are practical applications of vectors. This instruction involves 2 vectors, one pointing east with a magnitude of 2 blocks and another pointing north with a magnitude of 3 blocks. Each vector gives a clear and concise direction. Vectors provide a concise way to represent these directed movements. They simplify complex paths into manageable segments.
But vectors aren't limited to physical space. They can be applied in various fields beyond our immediate perception. They can represent any quantity with both magnitude and direction. This versatility makes them invaluable in numerous disciplines. For instance, the velocity of a car can be represented by a vector, where the magnitude is the speed and the direction is the heading. This helps in understanding motion dynamics. Similarly, a force acting on an object can be depicted as a vector, with the magnitude representing the strength of the force and the direction indicating the line of action. This is crucial in physics and engineering.
Vectors are the building blocks of linear algebra, providing a powerful way to represent and manipulate multidimensional data. They are essential in solving complex mathematical problems. They allow us to visualize and analyze relationships between quantities that vary in both magnitude and direction, offering insights into how different factors interact, opening doors to understanding complex systems and phenomena. Vectors are not just mathematical abstractions. They are tools that help us decode the intricacies of the world around us.
In the theatrical production of linear algebra, vectors take center stage. They are the primary actors, playing crucial roles in various mathematical scenarios. But every performance needs a stage. Without a proper stage, even the best actors can't perform effectively. This is where vector spaces come in. They provide the essential backdrop, the environment where vectors can interact and perform their roles. A vector space is a collection of vectors that obey specific rules, creating a consistent framework for performing mathematical operations. These rules ensure that the space is well defined and structured. Think of a vector space as a set of rules governing how vectors behave. These rules are like the script in a play, guiding the actions and interactions of the actors. These rules ensure that vectors within the same space can be added, subtracted, and multiplied by scalars, ordinary numbers, in a meaningful way. This consistency is crucial for performing complex calculations. For instance, adding two velocity vectors in a vector space results in a new velocity vector, reflecting the combined motion. This is akin to combining two forces to see their overall effect. Vector spaces come in various dimensions, depending on how many values are needed to define a vector within that space. The dimensionality of a vector space determines its complexity and the types of problems it can solve. A two-dimensional vector space, like the one representing movement on a flat surface, requires two values, east-west and north-south components. This simplicity makes it easier to visualize and understand. In contrast, a three-dimensional vector space, encompassing movements in our familiar three-dimensional world, necessitates three values, x, y, and z coordinates. This added dimension allows for more complex interactions and representations. These spaces provide the backdrop for linear transformations, which are operations that stretch, rotate, or reflect vectors while preserving their fundamental properties. Linear transformations are like special effects in a play, altering the appearance but not the essence of the actors. Linear transformations are central to understanding how systems evolve and how information is processed within them. They allow us to manipulate and analyze data in ways that reveal deeper insights and patterns. Section 5, Linear Transformations, mirroring reality with matrices. In the grand theater of linear algebra, matrices take on the role of directors, orchestrating the movements and transformations of vectors within their vector spaces.
These transformations, known as linear transformations, are mathematical functions that map vectors to other vectors while preserving certain essential properties. Imagine a mirror reflecting your image. This reflection is a linear transformation, preserving the relative positions and sizes of objects while reversing their orientation.
Similarly, rotating a shape around a fixed point is another example of a linear transformation, maintaining the distances between points while changing their absolute positions. Linear transformations are at the heart of understanding how systems change over time. They allow us to model processes like the flow of heat, the spread of information, and the evolution of populations.
By representing these transformations as matrices, we can efficiently analyze and predict the behavior of complex systems. For instance, in computer graphics, linear transformations are used to manipulate three-dimensional models, allowing us to rotate, scale, and translate objects on the screen. By applying a series of matrix multiplications, we can create realistic animations and immersive virtual worlds.